Okay, we're on 26.2 resistance. We'll get started with the PowerPoint. If VB and VA are equal, then there is no potential difference and there is no current. But once you have VB minus VA equals some delta V, you will set up an electric field and you will get current. And that current is defined by the charge density, the charge carrier density, and Q is the charge, 1.6 times 10 to the minus 19 coulombs. VD is the drift velocity, and A is the area. So that's the current. Now we can define a current density, which is the current divided by the area. Well, if you just go to the equation up at top and you divide both sides by A, the area, you get the current density, J, but that leaves NQV sub D. So that's the charge carrier density times the charge times the drift velocity. That is your current density. Current density is also defined by this sigma E, where sigma is the conductivity and E is the electric field. So we'll see it in different ways. We'll see E is equal to current density divided by conductivity, J over sigma. And let's read this definition. For many materials, including most metals, the ratio of the current density to the electric field is a constant sigma, in which J over E is some constant sigma that is independent of the electric field producing the current. In other words, the conductivity is independent of the electric field. And conductors that obey this, or any materials that obey this, obey Ohm's law. That this is Ohm's law. We'll see other forms of Ohm's law. Now, we have the potential difference, delta V, maintained across the conductor, and it sets up an electric field E. And this field produces a current that is proportional to the potential difference. So delta V is equal to EL. In previous chapters, we used delta V equals to ED, where D is the distance. And delta V is also, since E is equal to the current density divided by conductivity, delta V is equal to L times J divided by the conductivity sigma. And since J is also equal to I over A, we have L over the length divided by the conductivity divided by the area times I is equal to the resistance times the current. So L over divided by conductivity times the area is equal to the resistance. Now we're going to learn a different form using resistivity, but this is also a legitimate formula for resistance. We're going to learn that resistance is equal to delta V divided by I. So that is Ohm's law, but it takes many forms. If you just play with this formula, you'll see that R is equal to delta V divided by I. Delta V equals R times I, and I is equal to delta R. I'm sorry, I is equal to delta V divided by R. So those are the three equations that you're going to use for calculating Ohm's law. And the resistance is expressed with the capital letter omega, and we call it ohms. 1 ohm is equal to 1 volt per amp. 1 ohm is equal to 1 volt per amp. Reading resistors. Now, if you were in the lab on Wednesday, we covered this a bit, where we learned the color bands, black, brown, red, orange, yellow, green, blue, violet, gray, white, and then the gold, silver, and colorless are the tolerances for the values. In other words, the one we're looking at here, yellow, violet, black, gold, that's a 5% tolerance. And what values do we see? Well, the 4 and a 4 and a 7 and a black. So if you look at the formula, the resistance is equal to 10 times C1, so that's 40, plus C2, that's 7, times 10 to the 0 power, because that's black, so that's 47 ohms. And so that's, you don't have to commit that formula to memory. You'll get used to it as we use more and more resistors, and we are going to be using resistors in future labs. Okay. Resistivity. The resistivity is equal to the reciprocal of conductivity. So rho is equal to 1 over sigma, and the resistor is equal to the resistivity times the length divided by the area. So remember when we had the formula for the capacitor is equal to epsilon 0 times the area divided by the distance separating the plates, and I said that's an important formula to remember because it helps you visualize how to handle capacitors in series and capacitors in parallel. It helps you remember how to come up with the C equivalent. Well, this equation, R equals to rho L divided by A, is also important for understanding how to handle resistors in series and resistors in parallel. And I'll discuss that in a later, when we get to resistances in circuits. You don't necessarily have to commit that to memory, but know that it exists. The resistance equals to the resistivity, rho, times the length divided by the area. Now, so let's imagine three different hoses. A big fireman's hose, with big diameter, inside diameter. Then a garden hose, it's about a 1/2 inch to 3/8 of an inch for a garden hose. And then imagine a very small Tygon tubing that only has like a millimeter inside diameter. And you hook those up to the same water source. Which one is going to flow more water? Well, the one with the bigger cross-sectional area. And that would be the fireman's hose. The hose would allow most of the water through it. It has the least resistance. So low resistance resistors, you can think of them as having a large area. The garden hose, it's going to allow water through it, but not at the rate that the fireman's hose is with. That's why firemen don't go around with a garden hose putting out fires. They need that large flow of water. And of course, the Tygon tubing would allow very, very small amounts of water to flow through it. Now, if you were to put those one after the other, the large fireman's hose and then the garden hose, then the little Tygon tubing, they would all be limited by the Tygon tubing. No matter how much pressure you put in the fireman's hose, it's going to be regulated by the small Tygon tubing, and that would be these three hoses in series. So we're not quite there yet. I'm just explaining. Okay, we have ohmic and non-ohmic materials. So here we have three resistors of different values. I'm not going to take the time to try to figure out what the values are, but just know that it's a linear relationship. It's a straight line. The current divided by delta V gives you a slope of 1 over R, so it gives you a straight line. If you put delta V in the y-axis and current on the x-axis, you get R. Anyway, so resistors, they have a linear relationship. Semiconductors, like a diode, they're non-ohmic. So the resistor is ohmic. The diode is non-ohmic. It will allow current to flow in one direction, but resist flow in the opposite direction. That's the purpose of a diode. It's kind of a protector for protector circuits. We also use it for rectifier circuits. We'll learn about that later. I think we will. Okay, a cylindrical wire has a radius R and length L. If both R and L are doubled, does the resistance of the wire increase, decrease, or remain the same? Now, notice that they didn't say area. If the area and length were doubled, then you'd have the same resistance. But let's talk about the radius. Radius gives you an area of pi r squared. So if you double the radius, you've quadrupled the area, and if you increase the area, it decreases. So the answer here is decrease. Now, in this figure, as the applied voltage increase, does the resistance of the diode increase, decrease, or remain the same? Well, as you increase the delta V, you can see the current increases, and not in a linear fashion, so that the resistance of the diode decreases as you increase the voltage. And that's it. We'll stop there and go on with the model. That's 26.3 in the next one, the next lecture.